has us showing carbohydrates as Fischer projections. We'll talk about how to draw those and what those look like. Okay, so it's not going to feel like this at first, but I assure you Fischer projections are a simplified system to draw stereoisomers that show 3D representation. So typically when you have a complex molecule, it's going all over the place. These can be sometimes difficult to draw, okay, if you think of your skeletal structure. Drawing those, what you're looking at is glyceraldehyde, where in your wedge and dash notation, your wedges, the vertical bonds, are going to be going away from you, whereas your horizontal bonds are going towards you. So if we were to look at this as a molecule that I've built, those vertical bonds are going away from you. So if I turn those, they're all now facing back, and this is hard to see on the camera, they're facing back or away from you. So they're all kind of curled in back towards me. Notice that these horizontal bonds are coming out and towards you. Okay? If I were to flatten this, the backbone or the vertical bonds, if I were to flatten this, now suddenly it looks more like how we would draw this on paper. Okay, where my horizontal bonds now look like they're going straight horizontally and my vertical bonds are just straight up and down. Play with your model kits at home, that'll help. So the way that we draw this, again, if you remember back to our talk on chirality, if we want to show a chiral center or a carbon that has 4 different groups on it, we show that at the intersection of 2 lines. So the carbon that would be right here, we know is chiral because it has 1, 2, 3, 4 different groups. So Fischer projections are a way to show chirality. You may see that top carbonyl drawn like this, shorthand, that's a lot easier, or you may see it drawn all the way out. This is what it actually looks like. Either way, though, we do not draw the intersection of 2 lines for this carbon because it's not chiral. It doesn't have 4 different groups. Same thing with the carbonyl. Having a double bond immediately means you can't have 4 different groups, so it's not chiral, so we don't show it as an intersection of 2 lines. When we talk about carbohydrates, we will classify them as being in a D or an L form. So these are the 2 enantiomers that exist, and we're using one of the carbohydrates that you have to have memorized for the structure. We're using glyceraldehyde as the most simple one. In order to determine if you're working with D-glyceraldehyde or L-glyceraldehyde, you're going to look at the chiral carbon closest to the bottom or farthest from the carbonyl. So here's my carbonyl. Okay, this is the only chiral center I have. It's the furthest one away. This 3rd carbon is not chiral, so we won't look at that. So we look at that carbon closest to the bottom. If the OH group is on the left, then it would be the L form. If it's on the right, it's on the D. So here we have the OH group is on the right-hand side, so we would classify this as being D-glyceraldehyde. And the enantiomer, or the non-superimposable mirror image of it, would be L-glyceraldehyde, where the furthest away chiral carbon has the OH group on the left. The way I keep these straight is I literally remember L is for left. So if the furthest hydroxyl group from the carbonyl is on the left, then you have the L form of that carbohydrate. One struggle that we have, glyceraldehyde is an easy example. You have 1 chiral center with 1 OH group. The mirror image is pretty easy to see. But when we're talking about, say, a hexose that has 6 carbons on it, drawing the enantiomer becomes a little bit challenging. So when we say it's mirror image, it is the mirror image. We're talking about every single chiral center is the mirror image. So starting at carbon number 1, these don't matter. These cannot have mirror images. They're not chiral. Doesn't matter which side your carbonyl is on. But starting with carbon number 2, notice that my hydroxyl group is on the right. It's closest to the mirror. So the enantiomer should have that OH group on the left, closest to that mirror, just like a mirror. Carbon number 3, the OH groups are furthest away from the mirror. They are opposite of each other. They're the mirror images. And this happens for carbon 4 and carbon 5, which is our last chiral carbon. We don't care about non-chiral carbons. But for those 4 carbons in the center that are chiral, we expect the OH groups to be mirror images of each other. So every single carbon has to have that mirror image, not just the bottom one. And looking at the carbon furthest from the carbonyl, we can determine that the OH group on that carbon is on the right. This is the D form of the sugar. Whereas here we have the hydroxyl group on the left. This would be the L form of the sugar.